Today's lesson's over section 4.1, where we will be talking about related rates. Now, in a related rate problem, we have a goal of being able to find the rate at which some quantity is changing by relating it to other quantities that we know. Now, there is a kind of several step process that goes with this, and so kind of go through that for this first example, but first step is being able to read the problem. So for this first example, let V be the volume of a cylinder having height h, radius r, and assume that h and r vary with time. At a certain instant, the height is 6 centimeters and increasing at 1 centimeter per second, while the radius is 10 centimeters and decreasing at 1 centimeter per second. What is the rate at which the volume is changing at that instant? Okay, so reading the first problem, being able to identify the good information, and then using a diagram to help kind of facilitate what we need to do or what information we have is always good. Sometimes you won't be able to, which is fine. Then identifying the rates of change or things you do know. So we know the height, the radius, we know the height as time changes. We know the radius as time changes. Then you need to identify the equation or formula that you need to use to represent this. So in this case, it'll be volume, which is pi r squared h for a cylinder. Then once you've identified all those four things, now we get to differentiate our formula. And so that gives me the following thing in step 5. And then notice that we have several of those values that we've stated that we know, so we just plug those in for step 6. And once we simplify, then we're able to find the answer, which in this case is negative 20 pi centimeters cubed over seconds. But then we always want to answer the question in a sentence. So the volume is decreasing at a rate of 20 pi centimeters cubed per second. Now we want to be able to move on to example 2, do the same thing. So let A be the area of the circle of radius r that increases with the time t. At a certain instant, the radius is 5 centimeters and increasing at a rate of 2 centimeters per second. How fast is the area increasing at that instant? Okay, so here we're talking about the area of a circle, so we can use that to help us kind of depict what's going on if we need to. Now also, like I said before, some of these problems are not going to have pictures that kind of relate to them, so it's okay if you don't have, like, you're not able to draw a circle or like whatever figure that's going on, okay, because it may not be possible. But here I know the radius, I know the rate in which the radius increases with respect to time. I would like to know how fast the area is increasing with respect to time at that instant. So since I'm talking about a circle, the formula would be area equals pi r squared. So now I get the derivative of the area with respect to the time, and that equals 2 pi r, I'm just using the power rule there, times dr over dt. And so now I can start plugging in values that I know. So I know the radius, which is 5. I also know dr over dt, which is 2. So plugging those two values in, I get the value of, it looks like 20 pi. And so since we're talking about area, and that would be centimeters squared per second. And so then now I want to answer my question. So here the area of the circle would be increasing at a rate of 20 pi centimeters squared per second. Now looking at example 3, it says that let C be the length of a diagonal of a rectangle whose sides have lengths x and y, and assume that x and y vary with time. If x increases at a constant rate of 1/2 foot per second and y decreases at a constant rate of 1/4 feet per second, at what rate is the length of the diagonal changing when x is 3 feet and y is 4 feet? Okay, so here we're talking about a rectangle, so I kind of want to draw that. And then draw in the rectangle or the diagonal there. And so we can kind of label the diagonal however we want. So I think Z would be a good one since we're using X and Y for the other sides. So because that creates a right triangle, I'm able to use Pythagorean theorem here to help me out. I know what dx over dt is, which is 1/2 foot per second. I know the dy over dt, which is negative 1/4 feet per second. Notice that they also use the words increasing and decreasing, so that's trying to suggest whether it's positive or negative for your rates of change. Obviously, x is 3, y is 4. Since I'm going to use Pythagorean theorem here, I can kind of set it up so it's going to be x squared plus y squared equals z squared. And I want to be able to find dz over dt. Okay, so here I'm able to take the derivative, so 2x dx over dt plus 2y times dy over dt. Sorry about that. That should be dy. And then equals 2z times dz over dt. Okay, and then we can start plugging in values. So that gets me 2 times 3 times 1/2 plus 2 times 4 times negative 1/4. Yes, that's supposed to be dy. And then here, now I get a little trip or hitch in my process. I don't know z yet. I need it, but they didn't really give it to me. But they did give me enough information based on where it was at that I could find what z was with my original information before you take the derivative. So sometimes this happens, and so still using our same formula, I can plug in the values straight up, 3 and 4, and then that allows me to use Pythagorean theorem still to be able to find what z is. And so here, obviously doing the work gets me 5. Remember that because it's an actual figure with lengths, it has to be positive 5, not negative 5. So I can plug that in. Now I can complete my process. So here the 2 and the 1/2 cancel out. 4 and 1/4 cancel out. So it leaves me with 3 minus 2 equals 10 times dz over dt. And then that gets me 1 equals 10 times dz over dt. And I can divide both sides by 10. And that gets me 1/10 feet per second for my change of the length of the diagonal when you have all those other things going on. So the diagonal of the rectangle is increasing, since it's positive, at a rate of 1/10 feet per second. Now notice that the sentences don't have to be super long. They can be very short and sweet to describe what's going on. But that's really your answer. It's not we circle the 1/10 part. It's the sentence that we want to circle. So here example 4 says a spherical balloon is to be deflated so that its radius decreases at a constant rate of 15 centimeters per minute. At what rate must air be removed when the radius is 9 centimeters? Okay, so here I have a sphere drawn, and then the formula for the volume of a sphere is V equals 4/3 pi r cubed. I know what my radius is, which is 9 centimeters. I also know the rate at which my radius is decreasing by, which is negative 15 centimeters per minute. And then from here, I can take the derivative. I only need dv and r, so I'm not going to have the same thing that happened in example 3. So here, 4/3 pi is a constant. It stays there because it's multiplied. So the derivative of r cubed is just power rule, so it's 3r squared. I can simplify that a little bit, so it gets me 4 pi r squared. And then I can start plugging in values that I know. So I know that r, which is 9. And then I can plug in my dr over dt, which is negative 15. And then I can simplify. So obviously 4 times 9 squared, which is 81, times negative 15 will get me a value of negative 4,860 pi centimeters cubed per minute. Now, I usually want you to plug these in and make them values. I know the first example had pi in our answer, the first two anyway, but we usually actually want a real number there. So it's decreasing at negative 15,268.14 centimeters cubed per minute. Since we're talking about real things, it doesn't really truly make sense to leave them with pi. So I'm going to want you to have them as a decimal there. So our sentence for our final answer will be, the spherical balloon is deflating at a decreasing rate of negative 15,268.14 centimeters cubed per minute. Okay, thanks.